Welcome back, everyone. So in this video, we're going to be talking about angular momentum. All right, what we're going to do is just kind of introduce the idea and then move on to the conservation of angular momentum. So let's start with the general idea. Well, angular momentum is essentially just the rotational analog to linear momentum, right? So we talked about linear momentum being the quantity of motion. Well, angular momentum would be the quantity of rotational motion, right? It's not really a definable thing beyond that. Maybe we can talk about its equation, which we'll do now. Okay, so for the symbol for angular momentum, for who knows why, is a capital letter L, right? So we have a capital letter L, that is your angular momentum, okay? Now, if you remember, for linear momentum, it's mass times velocity. Well, for angular momentum, you'll have the rotational analogs to that. That's your rotational inertia, which is the rotational analog to mass, times your angular velocity, which is the rotational analog to velocity. So here we have angular momentum equals rotational inertia times angular velocity. Now, I can take this equation and write it in another way. In order to do that, though, I've got to give you a couple kind of givens almost, right? Let's say that our angular or our rotational inertia is mr squared, right? So the mass of the object times the radius squared, right, which is the generic version of the rotational inertia equation. Any other rotational inertia equation will be something like this: 2/3 of that, 2/5 of that, whatever, right? But this is the general one that can work pretty much for anything. Okay, so let's take this, and we'll say that our angular velocity is our linear velocity divided by the radius, right? This is one way we can calculate our angular velocity. All right, so what I'm going to do is I'm going to say L, I'm going to kind of put this off to the side here, L equals I times omega. Right, well, we say I is mr squared, and omega is v over r. Okay, so we have L equals I times omega, and that will equal, when we substitute these things in, I is mr squared, omega is v over r. Well, this r cancels out this r, and we're left with mr times v is our L. We rearrange this a little bit. We can say that L equals m, mass, times v, velocity, times the radius. Okay, well, we just said a couple minutes ago that mass times velocity is your linear momentum, so we're left with p times r, lowercase p for your angular momentum, times the radius. Right, so there's two ways that we can write the equation for angular momentum. Okay, L equals I times omega, L equals mvr, which is momentum, linear momentum, times the radius. Cool. Now, another thing that we want to kind of bring up that goes along with this idea of angular momentum is the conservation of angular momentum. Okay, just like with linear momentum, angular momentum and its conservation is one of the most important concepts in understanding how the universe works, right? By understanding how angular momentum is conserved, we're able to understand why our planet revolves around the sun, why our planet rotates on its axis, so on and so forth. Now, simply put, just like with linear momentum, we say that the angular momentum before equals the angular momentum after. Okay, so something will happen, and the angular momentum before that thing happens equals the angular momentum after that happens. And once again, it's important that it has to be a closed system, meaning there's no outside torque. Right? If you have something spinning and then somebody not part of the system comes by and spins it more, right? That's not going to be a conservation of momentum type of situation. So let's kind of continue with this. We have I times omega all before, Oops. Let me rewrite that, sorry. It's gigantic. I times omega before equals I times omega after. Okay. L before equals L after, which means I omega before equals I omega after. Right? What this means is if you change the rotational inertia, the angular velocity will change accordingly, right? To make sure that these two things are the same. Okay. Now, in another video, we're going to go through a few different scenarios about angular momentum and its conservation. So keep an eye out for that one as well. This video was just to kind of introduce those topics, give some basic notes on that. Okay, so until next time, I'll see you later.